a global initiative probing frontiers of particle physics. He also spearheads pioneering projects in quantum technology, including the Atom Interferometer Observatory and Network, AION, and the Atomic Experiment for Dark Matter and Gravity Exploration in Space, EDGE. His research not only deepens our understanding of the universe, but also brings together international experts from diverse fields such as astrophysics, quantum technology, earth sciences, cosmology, geodesy, fundamental physics, and expanding boundaries of what we know about time and space. Professor Buckmueller's community building efforts include the terrestrial very long baseline atom interferometry and possible experiments that will require an underground laboratory like SURF. Today's topic is very timely, as the 2025 International Year of Quantum Science and Technology recognizes 100 years since the initial development of quantum mechanics. Now, let's get set to explore the universe with quantum technology, the new frontier in physics, with Dr. Oliver Buckmueller. Take it away.
Thank you very much, Jared, for the invitation. So let me share my slides with you. I hope you can see them. You should be able to see my slides now. Is that correct? Can you?
Yeah, we can see them now.
Okay. Let me do full screen. Full screen? Looks
great.
good, yeah?
Yep.
Perfect. So again, thank you very much for the invitation. It's a great pleasure to be here today on Zoom and to discuss with you what I think are very interesting opportunities of exploring the universe with quantum technology. But before I come to the quantum technology part, I would like to show you here in this slide some of my personal shopping list, if you like, concerning open questions in fundamental physics. There are several very interesting ones, and everyone can have his or her shopping list. But one thing is very clear, that I think in the last 30 to 40 years, I think mankind really has developed an extremely strong research program of utilizing different technologies to go after these open questions in fundamental physics and successively starting to answer them. Today, I would like to show you how, in particular, one type of technology could be complementing that portfolio of very interesting activities which we have. For example, collider experiments in the US at CERN, which I have been participating in for a long time. And I think fundamental physics could benefit also here from quantum technology applications. Now, as been pointed out, it is the year of quantum this year, so it's really marking 100 years of quantum physics. So it all goes back to the beginning of the 20th century, as you can see here in this slide, where in particular two gentlemen, Heisenberg and Schrödinger, but aided by several other high-profile physicists like Albert Einstein, but also Pauli, started to develop this very fascinating theoretical understanding of how we believe the macroscopic and microscopic world actually is behaving. And today we're referring to that as quantum mechanics. This is something we're teaching already to undergrad students at many different universities, as a matter of fact. After that invention of the theoretical framework, it took several decades before first real-world applications came out of it, like, for example, the transistor, then the hard disk, and followed by the application of laser and laser light. So this is what people today, I think, refer to as the first quantum revolution. However, I think there's good reason to believe that we have entered, as a matter of fact, probably already 10 years ago, what people often say the second quantum revolution. And that goes back to the enormous improvement we have been making in that technology, which is in particular relevant towards what's being referred to as quantum sensors. And in my talk, I will introduce to you two quantum sensors, which in the last 10 to 15 years really have undergone a rapid development. And this is atom interferometry and atomic clocks. And they all now come to a level where many people believe that they are ready for real world applications, eventually then also leading to the next step, like quantum computing, unlocking quantum advantage, and so on. And today, I like to introduce to you of how these quantum sensors can also be used in order to search for open questions in fundamental physics. In particular, I have picked one of my open questions, which I think is most illustrative to demonstrate the potential interest we can have with these quantum sensors. And the question I've chosen here is, what can gravitational waves tell us about the universe and its fundamental laws, and in particular, how these fundamental laws might have been impacting the beginning of the universe? To come to this, I should also point out that it's not only 100 years of quantum physics development we should be celebrating, but it was also in parallel really a century of general relativity, to be honest, which has been developing more or less in parallel to the quantum world understanding. And for general relativity, and that obviously goes back to the development of special relativity and general relativity from Albert Einstein. So according to Einstein theory, gravity is not a force, but it really relates to the curvature of space-time. So in that understanding, very different than what we would formulate today in terms of a quantum field theory. And to put it in the words of John Wheeler, is matter tells space how to curve and space tells matter how to move. And that means if you have very massive objects in the universe which are traveling through space-time, like for example black holes, then these massive objects will start to create what we refer to as ripples in space-time, or to be more precise in a scientific term, to generate gravitational waves. The existence on the postulation of gravitational waves, which are these ripples that massive objects can generate at various different timescales of our universe, go back to the general formulation of general relativity by Albert Einstein. An intrinsic concept in the mathematical formulations and searching for them was also a very interesting aspect in, again, validating the correctness of general relativity. Now, how would this gravitational waves be formed? There are very different sources. Here I'm showing you really now a type of a black hole merger. So this is using a video from Caltech and LIGO, which shows you the dance of two very massive objects in our universe as they are being captured in their gravitational field, and then start to generate these ripples in space-time, as you can see here. And because these ripples in space-time will take away energy from this die object, effectively, the rotation will start to collapse eventually and comes to a merger, which, as you will see here now in the video in a second, will then effectively lead to a final ripple in the space-time continuum as we understand it, which is then the end of the generation of the gravitational wave. And that's what we typically are measuring today in LIGO and Virgo, the last chirp of that merger. So that was a video that illustrates how such gravitational waves are being generated. Now, the effect to measure such a gravitational wave is really incredibly small. So we had to build extremely sensitive instruments, which, as I will show you, are laser interferometer instruments to really measure it. But to illustrate such an effect, I'm going to go back to the first observation of a gravitational wave that LIGO has done in 2016. It was a gravitational wave that was originating from what we believe was a black hole merger. So two massive black holes, each of them having 30 times solar masses. So that means 30 times the mass of our sun, which had this dance and then eventually then were merging at the end. So if you use this and plug them into the calculations of general relativity, you can calculate how big the impact of such a black hole merger would be on the length scale of the space-time continuum. So if you imagine you would have had a meter as a measurement for your instrument, then the impact of the change of length this gravitational wave would have caused is at the level of 10 to the minus 21. That's the so-called strain sensitivity we're using to characterize sensitivity of laser interferometer experiments. So at the level of 1 meter, it would have been 10 to the minus 21 meters of variation we had to observe. Now, fortunately, LIGO and Virgo are experiments which are stretching over kilometers. So the effect really is at the level of 10 to the minus 19 meters we had to measure. But still, 10 to the minus 19 meters is an incredibly small number. And just to illustrate this incredibly small number we have to measure, let me give you a little illustration here. So this white line you can see here is now our reference system. Let's call it the meter, ballpark, depending where you want to look at. So now we're dividing that meter by a factor of 10,000. Then we are coming to about 100 microns, which is typically, the width of a hair. If we continue dividing this by a factor of 100, we're reaching typical wavelengths of light, which is around a micrometer. If we again divide that by a factor of 10,000, then we are coming to the scale of an atom, the diameter of an atom, which is around 10 to the minus 10 meters. If you again divide by a factor of 100,000, then you're coming to 10 to the minus 15, which is the typical diameter of a proton or a neutron, which are forming the nucleus of atoms. And if you then again divide by a factor of 10,000, you're reaching the level of sensitivity LIGO had to have to measure that variation of that gravitational wave that was generated roughly 1.3 billion years ago, and then arriving in the LIGO and Virgo detector with a variation to be measured at the level of 10 to the minus 19 meter. So we're really looking here at incredibly sensitive instruments, and quite rightly so. I think the three gentlemen here were recognized for their incredible work and investment into this development of these instruments with the Nobel Prize in 2017, following the first discovery of gravitational waves in LIGO and Virgo in 2000, or LIGO in particular in 2016. So this is now the laser interferometer landscape we're looking at Earth. So we really have started to establish quite a comprehensive experimental program for gravitational waves. So there's LIGO, the two LIGO detectors, there's the Virgo detector in Italy, there's GEO 600, which was a prototype built in Germany, and then eventually also our Japanese colleague have joined the game with the KAKRA experiment. And today these experiments are really operating in what I would call a network, a LIGO, Virgo, KAKRA network to measure gravitational waves from various different astrophysical sources. Now, with the observation of gravitational waves in 2016, I think we really have opened up a new window of looking into the universe. So instead of making them now a real signal to be observed, we are now planning to use gravitational waves in order to learn more about what has happened at very different stages of the formation of our universe. And as you can see here in this picture, I think there is really good hopes that we could potentially detect gravitational waves in a really enormous range of frequencies, going from 10 to the minus 9 hertz, well beyond 10 to the minus 10 to the minus 4, 10 to the minus 5 hertz in various different corners. So these are the instruments we would like to do. A particular interesting frequency range is around, let's say, 10 to the minus 4 hertz to around 10 to the 3 hertz. And that's the frequency range I would like to highlight now and to discuss with you what kind of instruments we're having today planned to measure this frequency range of around 10 to the 6 to 10 to the 4 hertz, roughly speaking. So this plot now shows you in greater detail of how we characterize now sensitivity of our detectors in terms of characteristic strain. So that's the sensitivity level I introduced to you before. A gravitational wave could generate in terms of length wave variation normalized to the entire length. You see different curves here, green and brown and red. So these are basically showing you different redshifts of black hole mergers. So this is redshifts basically means how far you can look at the beginning of our universe. And you can also see different mass scales for black hole mergers. So there's a mass range of 10 to the 7 solar masses. There's a mass range for intermediate black hole mergers of 10 to the 4. And today our experiments, LIGO, Virgo, KAKRA, that's the brown colored curve here, have sensitivities of around 100 solar masses. So the game is now really to expand the frequency range coverage with more experiments. And we do have an interesting planned program already that's underway. So we are planning to extend our reach on terrestrial experiments by building, and the Europeans would call it the Einstein Telescope. In the US, I think it's called the Cosmic Observer. So this is a larger scale experiment with higher sensitivity than LIGO and Virgo. But we also plan, and that's under construction as a matter of fact, a laser interferometer experiment in space with 3 satellites. So this is the so-called LISA experiment, which is spearheaded by the European Space Agency, and now also supplemented with significant support from NASA. And it's meant to be launched around 2035, with first signals then hopefully be observed around 2036, 2037, if things are going well. Now, if you carefully look at that plot, as we would say in London, mind the gap. There's an interesting gap in this frequency range, which is often referred to as the mid-frequency range, which is very difficult to be covered with laser interferometer experiments for very different reasons. And when I saw this plot for the first time after the discovery of gravitational waves in 2016, I started to develop some ideas together with others of how we could potentially fill this very interesting gap, because that gap has certain properties for gravitational waves, and I will come to that in a minute, which is not only important to simply, fill the gap so that we can measure the entire frequency range, but also in terms of multi-messenger physics. Now, it happened to be that if you look at the technologies that's being available, that if you were to build and use one of those quantum sensors I mentioned at the beginning of my talk, which is so successful in its technology development, namely atom interferometry, and would basically incorporate that into a large shaft of several hundred meters up to a kilometer, you could start building an experiment, as you can see here now, with this overlap curve, which is referred to as ion kilometer, that could start filling in that mid-frequency range, that very important mid-frequency range. Now, why is this mid-frequency so important? Well, first of all, as I pointed out, if you want to use gravitational waves as a tool to understand more about the universe, then obviously having an incomplete picture in terms of a gap in the frequency is never good. So that's already one argument. But there's an even more important physics argument why the mid-frequency range is important, namely because it allows us to observe signals at the level of days, weeks, even months, possibly even a year or longer timescales. And that means that if we would have had, for example, a mid-frequency gravitational wave experiment when LIGO observed the last chirp of this first merger of bright black holes we have ever seen in mankind, that mid-frequency experiment could have followed that merger before it happened for several months. And based on that signal you would have seen earlier in the frequency range, before that merger would have happened, because of the rotation of Earth around Sun, you would have been able to make an extremely precise determination of where the signal would come from. And that opens up what we refer to as a completely new window of multi-messenger physics, because we would have had the ability to basically put all of our various different detection systems into that direction to start observing what else comes along with this gravitational wave mergers in terms of neutrinos, photons, and so on. So the mid-frequency range is really key in unlocking a comprehensive program for multi-messenger physics. And if we would have had an experiment at the time, multi-messenger physics today would definitely have taken our physics understanding to a completely new level. So that's another interesting motivation of why I would like to build and cover the mid-frequency range. Another aspect, and that's same as it is true for LIGO and Virgo, is that eventually you would like to build this atom interferometer experiments, not just one, but several of them, to really build on the redundancy and the different directions these experiments can have. And one of the things I will show later in my talk is a potential network between the US and Europe with 2 experiments, which is ION and MAGIS. Another important aspect to the technology, similar to laser interferometry, would be then eventually the highest sensitivity you will have is to bring this technology into space. And as this is something that takes quite some time to be developed, not only to get the technology space ready, but also now to start really developing full mission concepts. Already in 2019, we have been writing mission proposal design which we have been sharing with the European Space Agency, but also with NASA, and we're still discussing with them today how to best implement this. But that's obviously a long-term planning aspect, and it will not happen before 2045 plus. But it is an interesting option to really get ultimate sensitivity in the mid-frequency range. So if we were to have by 2045 such a space-based experiment, then we could, as you could see here in this blue line, even further extend our reach in the mid-frequency range regime, but also then really start covering other regions of that frequency parameter space. So that's quite an interesting physics parameter space such quantum technology could cover. Now, what is atom interferometry? I showed you the potential that atom interferometry can have if it's being realized on the large scale, but I would like to also give you a short introduction what actually atom interferometry is. And the best way to do this is to compare it with something we do understand reasonably well, and that is light interferometry, i.e. the tool we have been using to discover gravitational wave signals today, but it's also something we are teaching to our students in first and second year in physics. So in light interferometry, the active element is laser light. So you shine your laser light on the beam splitter, then the laser light takes two different passes with the help of mirrors. You are reconnecting this in the detection region, and because of the wave character of light, you will get something like light fringes. And from these fringes, then basically you can deduce whether or not something differently has happened between the two different arms. Like, for example, the variation at the level of 10 to the minus 19 in LIGO when a gravitational wave passes through. Atom interferometry is conceptually identical. However, now the active element is not laser light, but it's actually atoms. And it's not only atoms, but it's atoms which are cooled to the lowest possible temperature. So it's really ultra cooled atoms. And we will not just have one atom. We are trying to use an ensemble of around 10 to the 6 to 10 to the 10 atoms in this ultra cold state. And then with the help of lasers, you can construct what we would refer to as beam splitters, so-called pi-half pulses, which enable you to separate that ultra-cold cloud of atoms into half of it in the excited state and the other half stay in the ground state. And with that, you're starting to open up then the two arms of your interferometer sequence. Mirrors can again be constructed from lasers with so-called pi pulses, in which you then flip the excited state into the ground state and the ground state into the excited state. And again, at the end of the sequence, you will have a beam splitter pulse, a so-called pi-half pulse, that then focuses you back on your interrogation and detection region. And what you then observe is not light fringes, but because of the particle wave dualism of quantum mechanics of the atoms, you're observing matter fringes or atom fringes because of the wave nature of quantum mechanics. And these wave fringes can be interpreted in the same way that the light fringes can be, and out of the phase change, you can basically then deduce whether or not something differently has happened between the two different arms. But for the technology to really reach the sensitivity level we would like to have, we are planning to combine atom interferometry with yet another very popular quantum sensor, and it's probably the most popular quantum sensor today, is so-called atomic clocks. Atomic clocks really, as I can show you in this plot here, have undergone an enormous technology development in the last 20 years. I mean, we're currently building one in my lab here at Imperial College, which is meant to be among the most precise, if not even the most precise clock ever been built so far. And they're really the instruments today which are measuring time to the highest possible level of accuracy. So if we would have had an atomic clock established at the beginning of our universe, which was 13.7 billion years ago, and we would have measured the time today of that clock, then it would have given us a precision and an accuracy at the level of less than 0.5 seconds, with which it would have precisely measured the beginning of the time of our universe. So these clocks are extremely precise. And we would like to harness this enormous precision of atomic clocks to combine it with the properties of atom interferometry to then really do atom interferometry, as we call it, on the clock transition, which is what we believe is ultimately being required to then reach the sensitivity to measure gravitational waves. But to introduce to you conceptually how we would measure gravitational waves, I would like to use atomic clocks because it is simpler. But at the end, as I just mentioned, you will integrate this with atom interferometry and makes the thing a bit more complicated. But the conceptual idea is the same. So in this Gedanken experiment, as we Germans would call it, we will have two atomic clocks. And you have to think of these atomic clocks really being far separated in space-time. So the clock on our left will become our reference clock, and the clock to our right will become our measurement clock. Now, these clocks are being made out of one species of atoms. In our case, this would be strontium, where the atoms will have a ground state and an excited state, and the separation of the ground state and the excited state is being given by a frequency omega alpha. Now, what I do at the beginning of my experiment is to use one common laser beam to synchronize my two clocks. So this is the so-called pi-half pulse or beam splitter pulse I was introducing to you before. So it splits the atoms, which are ultra cold in this clock, into half of them in the excited state and half of them in the ground state. And that's true for both clocks. Then I'm starting my experiment. The two clocks are traveling through space and time. And at the end, I'm reading out again with one common laser beam the two clocks. Now, what will happen is because of the quantum mechanic nature, and if you write down the Schrödinger equation for that, the excited state will have accumulated, as we call it, a phase. Now, that phase has two components. One component is that it is proportional to the frequency between the excited and the ground state, and the other one is that it is proportional through the time of your experiment. Now, if I measure back the phase, or if you like, the time of the two clocks, and compare the two, and nothing has happened between the two, then basically I will get a null measurement between the two. Now, what happened if my measurement clock and the space-time continuum of my measurement clock it was traveling through was exposed to a gravitational wave? Well, in that case, because of the strain of the gravitational wave, a small variation of length will have taken place. And that small variation of length, because the speed of light is constant, will immediately transform into what's referred to as a time dilatation delta t. Now, that time dilatation delta t will imprint on my measurement clock. And if I then, at the end of my experiment, again compare the two clocks, I will be able to measure back delta t. And out of delta t, I can then infer the properties of the gravitational wave, its frequency, its strain, and so on. So that's the conceptual idea of how we would like to measure with clock atom interferometry gravitational waves. Now, it happens to be that with the same experimental setup, and if there's another interesting open question in our universe, namely related to dark matter, that this experimental setup could also potentially give us an answer about dark matter. In particular, if dark matter is really ultra light, that means because, again, of the wave particle duality of quantum mechanics, you could see dark matter as a classical wave, which is penetrating, again, our space-time continuum. But now, instead of changing the space-time continuum, it will actually imprint on our atoms. It will change some of the fundamental properties of the atoms, like the electron mass, and also the alpha fine structure constant. But at the end of the day, you can think of it that it will imprint the classical frequency of my dark matter field on the variation of the excited and the ground state with a delta omega alpha. So now, if I again look at my phase, I will have again a change of my phase, but this time it's not imprinted on the time part, but on the frequency part. And again, if I compare the two clocks, then I will be able to measure back delta omega dark matter, and from that can infer properties of potential dark matter. So besides having a guaranteed signal to measure gravitational waves in the mid-frequency, it can also be serving as a search in a relatively large parameter space to whether or not ultralight dark matter is potentially being realized in nature, which obviously makes the whole thing quite interesting with the same experimental setup. Now, let's come to the real world, going away from Gedanken experiments into real applications. In order to really test that technology, the combination of atom interferometry with atomic clocks, I have been forming a consortium in the UK, which we have baptized ION, which really brings together several of the big UK powerhouses in terms of universities. So we have Liverpool University, we have the Quantum Hub in Birmingham, we have Cambridge University, we have Oxford University, we have King's College London, we have Imperial College, which is the lead institution, but we also have one of our particle national labs directly been partnering with ION, namely the Rutherford Appleton Laboratory. So this consortium is really meant to develop the underlying technology and to demonstrate by scaling it to significant dimensions like 10 and 100 meters, as I will show you in a second, that this technology can really be used in order to measure then eventually gravitational waves and possibly even detect ultralight dark matter. But right from the outset, and that I think makes it interesting for this talk, we were not only focusing on a pure UK development, but right from the outset, we're really partnering with our sister experiment, if you like, in the US, this Matches 100, which brings together some of the very interesting national laboratories and powerhouse universities like Stanford University, Johns Hopkins, Northwestern University, and Chicago University of building a LIGO-Virgo style partnership of developing coherently together the two underlying technology, but also then to build two experiments, one in Europe and one in the US, to have then really the redundancy being required to do all these measurements. Now, Matches 100, and you might have had already a talk about this, so I don't want to go too much into the detail, is currently being under construction at Fermilab. So there is really the idea to build a 100-meter prototype experiment at the Minus shaft, as you can see here. It's already a reasonably advanced state, with significant funding already being invested. Now, my understanding is that there are some issues at Fermilab, as we all know, and we don't want to go too much into the details here, but the construction is ongoing, and there is a horizon of the construction to be completed around 2027 or even 2028, depending on how it goes. But this experiment is ongoing, and the UK, in the context of ION, does make very significant contribution to this experiment already, as it's being listed here. So there is a significant amount of money from the UK side also being invested into Matches 100 and vice versa in a true partnership. And for that reason, we were very pleased that this partnership then really was put onto a much more formal and legal level in November 2023, when the former Fermilab director was signing together with our former director of our funding agency, STFC, at Fermilab, that legal agreement. I was present to represent the ION collaboration, and Jason Hogan was present then to represent the Matches 100 collaboration. So there's a real legal framework now for the UK and the US to work together, and I think it's a quite interesting development, which really shows you the direction in which that field is going from national initiatives to international initiatives. Now, the ION program is really very ambitious. It's a 4-stage program. The first stage was funded with more than £10 million, and it's now almost coming to conclusion. That was really to establish the prerequisite of the technology in the UK and start building prototypes that are scalable, as I will show you. And the next stage now is focusing of expanding that technology to start large-scale prototypes, even at the level of 100 meter and beyond. The ultimate terrestrial stage would be to build such an experiment in the kilometer scale. And for these shaft experiments that ION and Matches is proposing, we would need kilometer shafts. I will come back to that. SURF might be an interesting opportunity. And last but not least, but that's really several decades down the road, bringing that technology into space. So it's a very ambitious program that ION has. And that is showing you the members of the ION collaboration. There's a picture taken in Oxford in 2021. But the point I would like to make here is that for the first time, to my knowledge at least, this was really bringing together two very different physics communities in one place and under the head of one project, namely the fundamental physics or particle physics community, which is my background. I come from CERN mostly, but also have worked at Fermilab at SLAC, together then with the technology stakeholders, namely those who are developing atom interferometry and atomic clocks hands-on, so the quantum technology development. So it's really bringing these two communities together was quite an interesting observation, and working together with the very different backgrounds we're having. And I think today, all the early career researchers we're having now, and which went through 3 to 4 years of training in that collaboration, really now start to speak both of the languages, which I think is very, very beneficial. So we really have started here a new community that brings together both of those stakeholders. Now, what are the first lessons we have learned from the ION project in by now more than 30 months? One lesson, I think, which I believe is very important, is that there is not only quantum technology for high energy physics, or if you like, for particle physics, but there's also a lot to learn in terms of high energy physics providing to the development and synergies of quantum technology. That's one of the aspects I think we have learned in the ION collaboration, because one of the things we were charged with was to build 5 state-of-the-art ultra-cold strontium laboratories in the UK in parallel, which is totally unprecedented for the realm of quantum technology development, because people usually work in the lab and everything is being done in the lab. The first thing we from the particle physics community brought to the plate was to say, we have to centralize the key components of these laboratories and use our national laboratories to build the key components. And that is a completely novel ansatz that was very foreign to my colleagues coming from the field of quantum technology development. And in particular, we were focusing on 2 important aspects of these labs, namely the ultra-high vacuum system, which you want is the heart of such a laboratory, and the laser stabilization system, which, if you want, again, an analogy, is the brain of such a laboratory. All of those were built at our national laboratories, where we have vast expertise for this type of development. So the laser stabilization system was built at Rutherford Appleton Laboratory. 5 of them were built, they were all being tested, and then basically shipped to the various different laboratories. And the performance of them is unprecedented. And that was, again, something we could do because we were really having experts working on them and replicating then the work 5 times. The other, and probably even more tedious approach, was to do the full assembly, design, and construction of the ultra-high vacuum systems centralized. That's something cold atom people were not at all used to, and it took some time to convince. So we were really involving engineers and technician efforts. Again, something that's typically not been done in the realm of quantum technology, at least for now, into the business to do proper designs of this vacuum system so they could easily be replicated and baked out at one common place. And for that, we were choosing the Dasborough National Laboratory, which has huge expertise in vacuum systems in general. And with that ansatz, then we were able to really build 5 of those laboratories in less than 24 months, which again is unprecedented and was one of the biggest challenges. So we're building one at the Birmingham Hub, Quantum Hub, one in Cambridge, one at Imperial College, one at Oxford, and one at the Rutherford Appleton Laboratory. So here you can see the first delivery to Cambridge in 2022. So this is the vacuum system here on the right. This is how they look like. The next one came more or less at the same time to Birmingham Quantum Hub, because we were building them and baking them out in parallel in Dasbury. Then came the summer break. The next delivery then was in August to Imperial College, followed by Oxford University in October, and then Bral also in October. So you can see the delivery of these vacuum systems came more or less on block, because we were building and designing them centrally. In addition, the laser systems, the laser stabilization systems were being developed. So all the teams at the 5 different laboratories did not have to really worry about how to build a vacuum system or their laser stabilization system, but instead could really focus on what they are experts in, namely building up the laser systems in general, and also then the optic systems. And for that reason, when the components were delivered, very shortly after in 2022, and that's now October, all of those labs were able to observe what is called a blue mod. And that's the first stage of the commissioning of a lab, which is using strontium atoms for atom interferometry. Then almost a year later, the labs were fully commissioned. and starting to produce the first results. So this is basically now showing you atom interferometry on strontium atoms, which is common. Many people are doing this, but it's just part of the commissioning process. The next step then was to introduce large momentum transfer, so to kick the atoms not just with one H bar, but with several H bars to increase sensitivity. And last but not least, and that was the world's first, then to start integrating atom interferometry with the atomic clock transition of strontium, which is one of the most developed atomic clocks which we can build today. And that was a first observation of atom fringes in free fall on strontium-87. So that was the world first. But we took it even one step further, and that's a paper we're currently writing, which is meant to go into Nature, which basically demonstrates the entire setup of a differential gradiometer with clock atom interferometry to demonstrate the scaling of this technology to the level of hundreds and kilometer scale. So that's something we have been doing as the prototype system, and that is, as I said, a very important cornerstone to really demonstrate the technology. That's all been written up, and don't want to go too much into the details. Now, in all fairness, I've introduced to you ION and MATCHES, which are the two UK-US initiatives in close partnership, but there's much more national endeavors ongoing as we speak in the world. So for example, in France, there is currently a construction of a horizontal atom interferometer prototype system called MIGA ongoing. Our Chinese colleague with SAIGA are really making tremendous investments into their sites. They really look at both horizontal and vertical options of establishing atom interferometry with various different species for fundamental physics exploitation. Our German colleagues in Hanover have built a 10-meter tower for the same purpose. So there's a lot of interesting activities ongoing worldwide, which all of them are at the moment financed by several order of 10 million currency units each. So we're looking here really at a very significant investment volume, which is invested by national funding agencies. And one of the things I have always been worried about is that we are not talking enough with each other. So for that reason, we were bringing together all the stakeholders of these experiments together with what I would refer to the user community, those who would like to have and measure mid-frequency gravitational waves in two workshops. The first workshop was organized at CERN for terrestrial very long baseline atom interferometry. And then we had another workshop, which I was here organizing at Imperial College London in April. And out of that came a very interesting development that there's so much appetite in the world and in the users community today that we were forming a legal entity, which we refer to as the TVLBI protocol operation, which brings together 55 quite renowned institutions from 21 countries, which are now looking into the options of exploiting all these developments to start, establishing a roadmap of how such large-scale experiments could be built across the globe, similar to a LIGO-Virgo-style network, if you like. There's also an interesting development when it comes to observer states. Because of the legal framework we have chosen, some of the national laboratories were not easy to be joining in, but they are all basically now acting as observers in our collaboration. So we have the DLR, for example, from Germany, but from the US, we have Fermilab, which is one of our observers, and the Jet Propulsion Laboratory as well. So if there's any interest to join this collaboration on a observer status, as I happen to be elected as the chair of that collaboration, I would be more than happy to consider any requests, because we are really eager to be inclusive as possible for various different reasons. So that's an interesting development which is currently ongoing, which I think will shape the international landscape of large-scale interferometries for the next decade to come. One of the things we're discussing in this TVL community is obviously what would be appropriate sites to host such experiments. There's several considerations one has to take into account. There's noise level, seismic noise level, and so on. And for that reason, at our workshops, we have been reviewing already twice now potential site options. So we have in the UK Bolby Underground Laboratory, which is a national laboratory, which has been pitching to TVLBI the possible use of a 100-meter, but also kilometer shaft at the Bolby National Laboratory, as you can see here. We have CERN, which has entered the race quite prominently recently because there are quite a few support shafts which could be utilized for large-scale atom interferometer experiments, in particular the one I'm showing you here at PX46. And there has already been a very comprehensive conceptual feasibility study being launched by CERN, which we supported, which basically looked at the shaft and the various noise level environments, and also what would it take to refurbish the shaft so that it can be used for the experiment. So there's a lot of development now ongoing on site options, and we clearly have an interest to promote this, because one of the interesting things is, even with a 100-meter experiment, that if you reach the sensitivity on the cold atom side, you could start, as it's been shown here, open up already before 2035, before LISA or even an Einstein telescope could be realized, a new frequency range, namely the mid-frequency range, even with a 100-meter scale experiment. Obviously, kilometer scale would give you more sensitivity, but that's also longer down the road. We also looked at various possible sites then for the second stage, the kilometer stage. So we had a visit to Porto Alpina. It's a Swiss site in the Gotthard Tunnel. They were very open on the Swiss side to really give us access to it. And we're currently in very close discussions with them of how to bring this forward, to do some noise level measurements and so on, which would be important. We clearly also had other discussions. So we had SURF being presented at our first workshop and our second workshop. There's also Kalilo Lab, which has an interest on the kilometer scale. And there was quite a few discussions around the Stanford Underground Research Laboratory as being an interesting site on the US territory in terms of kilometer scale shafts. So there are several interesting options ranging from 100-meter to several 100-meter to the kilometer level, which could fill the purpose of a TVL-BI being built in the US. And for that reason, in May 31st, we have been following that call, also submitted a letter of interest from the TVL-BI into exploring further the options of building one of the potentially several large-scale atom interferometry across the globe. And that's something we will be continuing discussing now in the real protocol operation entity, and to see how to best take this forward. A few words at the end of bringing this into space. That technology in particular, I think, is suited for space. There are several aspects to it, but the most important one is free fall time. If longer you can hold the atoms in free fall time for their interrogation, as higher your sensitivity will become. It's even entering quadratically, as a matter of fact. So there is a lot to be gained of bringing that technology into space. For that reason, already in 2019, we had a very interesting workshop, out of which the EDGE proposal I mentioned to you came already, but we did much more. We developed even a roadmap of how the technology could be brought into space. And that roadmap is not just for fundamental physics, but really for various different other applications, in particular also for Earth observation. And that's one of the important aspects I would like to highlight at the end of my talk, which I think is important when we talk about this technology. This technology is ideally suited in space to measure the gravitational field of Earth. And some of the big limitations I see today is really the lack of precise data we have coming from space in terms of measuring equivalence of water height, as it's been referred to, or really resolving the Earth and the gravitational field of Earth to a very high level of precision. That suffers a lot, the input into climate models, and therefore the constraint on climate models of how potentially then climate change will unfold over the coming years and decades. And the upper plot you can see here shows you what you can do when you have classical, also non-quantum mechanic sensors, electrostatic sensors in space to measure the gravitational field of Earth. They have a drift, and also the resolution power is really terrible in order to resolve the Earth patterns very accurately when it comes to equivalence of water height, which would be a very important parameter to be fed into climate models. If you were to bring into space, and that's shown by the lower plot, as we discussed also at this workshop, quantum sensors with that capability, in particular an atom interferometry or an atomic clock, with relatively modest conception on precision, you could start resolving water height levels on Earth much more accurately. So that's one of the things outside of fundamental physics we're currently pursuing and having an interest to raise awareness of this and discuss with space agencies how to best bring this into space. Now, this brings me almost to the end of my talk. So this could now be a vision for 2045 when it comes of covering that important frequency range with various different atom interferometer experiments. But it's not only gravitational waves you can do, really. I showed you already the possibility of measuring ultralight dark matter, but in reality, there's also a lot of potential of using these experiments and the quantum technology potential to look for potential probes of dark energy and various other interesting physics. So there's a new, very exciting research avenue based on this quantum technology, which I believe is ahead of us. So I'll leave it here. Thank you.
Very good. Thank you so much, Professor Buckmueller. Wonderful talk on a fascinating topic. Let's check for questions. First of all, anyone wanting to raise a hand and ask a question? If not, I have a couple I can throw out as well. There was one here in the chat from Tom Regan, who was interested in some of the history that we have at SURF with the Deep Underground Gravity Lab, the collaborators from LIGO called Dougal, who were doing some initial Newtonian noise measurements at our lab starting all the way back in 2008. You mentioned some opportunities for SURF. I was wondering if you wanted to expand on that a little bit in terms of maybe both options for vertical and potentially a horizontal real estate that could be leveraged for some of these 100-meter or kilometer scale atom interferometry projects.
Yeah, I think as we also have written in the letter of intent we sent to you in May, SURF certainly is a very interesting site, offering both vertical and horizontal opportunities. And we would be very keen to explore more, as we do with other sites right now. So there is studies ongoing for Bowlby. There are studies now ongoing on the CERN side, but there's also now studies ongoing in Canfranca in Spain for the underground laboratory. And we would be more than interested to bring that level of investigation, evaluating what kind of Newtonian noise studies are already available, looking at the various different noise aspects where I'm sure you have already a lot of measurements and compare them with different sites. That would be the first starting point to evaluate how useful the site would be for atom interferometer, even so I have a feeling that it would be quite useful. What kind of shafts and what kind of horizontal infrastructure would be available. This type of things would be the next step to explore. And for that reason, as I pointed out, it might be quite interesting for you at SURF to consider to join the TVLBI, maybe not as a full member, but as an observer, to really give input to that process, which is now starting in earnest to build this entire collaboration with the 55 institutions from 21 countries, which, by the way, has very strong, as you saw, US representation also in it. So I think having SURF as an observer in there as a national laboratory, which can be a potential host site, could help us to facilitate the next steps in terms of doing the studies we would need to do to start evaluating whether or not this would be a good site.
Very good. Yeah, excellent point. Other questions? I know the European strategic planning is kicking off, sort of equivalent to SNOMAS for those in the US who are familiar with that community input process. I don't know if you want to say a few words about expectations on how this science might fare in that strategic planning process.
Again, we have this TVLBI collaboration. We're currently preparing an input to the European strategy. We are not only preparing this from the TVLBI collaboration per se, but we also try to channel that through the national routes. So there's always national routes because it's a European strategy. So there are several countries which can feed into that. So in particular, UK, Germany, but also France and Italy are prioritizing now this type of quantum technology development. CERN by itself has started to invest more into quantum technology, maybe not the same as Fermilab is right now, but the Quantum Initiative at CERN is looking into it, and CERN is one of the big drivers for the European strategy. So there's a lot of things ongoing, and we're quite hopeful that large-scale atom interferometry, both for ultralight dark matter, but also for gravitational waves, will find the appropriate place in the European strategy. By the way, both ION and MATCHES also have submitted LOIs to the SNOMAS process, which you mentioned earlier. So we're really trying to bring this on the map, and I think we're quite successful so far.
Great. We do have one other question here in the Q&A, and I can go ahead and ask it. It is, it gets back to the measurements that I alluded to earlier with Dougal and the Newtonian noise measurement facility. Are those useful to the community? Are they informing some of the plans either for your work or for the Einstein Telescope and Cosmic Explorer, those types of projects as well? I don't know if you can say a few words on that.
Yeah, I mean, certainly that would be helpful. Now, the problem is if you're doing horizontal experiment, you know, that you are interested on the gravitational gradient noise, or Newtonian noise, as you would call it, which is basically, you know, or seismic noise, which goes horizontal. Now, what we are also interested in is on the vertical change. So what we have been doing is to measure for approach, like at CERN, for example, we have measured at the beginning of the shaft, we have measured at the end of the shaft, we were even lowering some instruments along the shaft to better map out how the gravitational gradient noise is changing as you go with the height difference. So that may be measurements which are not yet available, or they may be available. I do not know. So one would really have to look at what type of measurements are currently being available at SURF. And the experience we have made is that for several of national laboratories, there's a lot of wells of data already being available, which one just have to look at and to start analyzing and not to retake. The exception was Bowlby, where not much of those data were available, and where we are currently running a measurement campaign. The way I described it, at the top of the shaft, at the middle of the shaft, and at the end of the shaft, to have a better understanding of how gravitational gradient noise or seismic noise is changing. The specific thing about Bowlby is also that it is directly at the coast. So we need to understand how waves are impacting the infrastructure and this kind of things. But I'm pretty sure if someone is knowledgeable about your database and what type of measurements you have done already, that as a first stage, we could just analyze these data and see how appropriate they would be for an atom interferometer experiment in the frequency range we're being interested in, which is, again, an important thing because, you know, Einstein Telescope will sit in a different frequency range. They're typically looking at sensitivity ranges of 10 Hertz and higher, while our sensitivity range would be at a hertz and lower, so a tens and the hundreds of a hertz. So again, it's different frequency ranges you're being interested in, where you need to understand how the seismic noise and gravitational gradient noise is impacting. But I'm sure the data do exist for first order evaluation for sure.
Right. And maybe our last question, as we wrap up here, on a question on atomic clocks. Don't we need atomic clocks based on different isotopes to separate the possibility of ultralight dark matter from gravitational waves in an AI? What's the status there?
So if you use atomic clocks without atom interferometry, if you just use atomic clocks to measure ultralight dark matter, the only way you can really do this is by having two different isotopes in which you then compare, because the isotopes, the coupling of the dark matter on the isotopes will be different. Now, if you run atomic clocks in the environment as we do it with atom interferometry on the clock transition, so it's not really an atomic clock as I introduced to you, it was just making it simpler, then you have sensitivity to scalar dark matter. Scalar dark matter in exactly the same way as you would have with a gravitational wave. There is no need for different species. Now, if you were, for example, to look for vector dark matter, then running dual species atom interferometry, so one with strontium and the other one with ytterbium, for example, which also have different mass scales, that would definitely be required and more beneficial. But you could also run with just different isotopes of the same atom. So it depends on the type of ultralight dark matter you're interested in. The one I showed you, which can use the same setup, then gravitational waves is scalar ultralight dark matter, which is one of the most prominent models, but there's also vector and axion dark matter, obviously in the same low mass range.
Very good. Thank you. Thank you. Well, with that, I think we'll wrap up the question period. Quick reminder that this talk is available to view and share on YouTube and Vimeo, and also at the website institute.surf/deepertalks. Next month's Deeper Talk will be on March 12th at the regular time, 9 a.m. Mountain Time. And the topic here will be the final results from 1 decade of operating Majorana with featured speaker, Dr. Ian Gwynn. Your feedback helps improve the program, and we appreciate any suggestions for speakers and topics for future talks. Please fill out the short survey that you will receive immediately following the talk. It will occur on Zoom as well as in your email. Once again, thank you, Professor Buckmueller. Thank you, everyone, for attending. Over and out. Thank you.